This session will be talking about air source heat pumps and efficient new construction in Minnesota and how it can help us lead to the clean energy future. So today we'll do some introductions of Phil and I as your presenters. Then we'll talk about Center for Energy and Environment, the organization that we work for. I'll dive into our cold climate air source heat pump research. And then I'll be passing it off to Phil to talk about single family case studies, as well as energy efficient multifamily buildings and best practices. So I'm Isaac Smith. I've worked at Center for Energy and Environment for a little over 9 years. I've been working in various residential programs that entire time. So I did some quality assurance programs with insulation contractors and did some training around that. I've also managed our residential energy audit program where we're in around 6,000 to 8,000 homes per year. And now I'm focused on new residential energy programs, kind of looking into the future about how we can deliver savings to customers. Phil, do you want to introduce yourself?
Hi, I'm Phil Anderson, also a CE. I've been here about 5 years now. Before that, I did low-income weatherization for about 10 years. At my time at CE, I've run new homes programs, so I work with builders, developers, homeowners, architects, trying to help them make more efficient homes. So we do HERS ratings, testings, a bunch of other energy certifications. We also run some new home programs for some utilities, and then also work on existing homes for quality assurance. So after people insulate their homes or do other upgrades to their homes, we go out there and take a look at that and make sure it was done correctly, and also do some training with contractors as well.
All right, thanks, Phil. So I wanted to talk about Center for Energy and Environment. We're a nonprofit based in the Twin Cities area. We've been around for over 40 years, and we really started out by kind of focusing on research, looking at different technologies to see how energy efficient they were, how well they worked in the field, and how much savings they delivered to customers. And we kind of quickly moved into programs and program implementation to help really bring that research to the market and to our communities, so help deliver those energy savings to the customers that we work with. And programs are a big part of what we do now. Like I said, we do home energy audits around 6,000 to 8,000 per year. We also have a small business lighting program and small business program where we help business owners save money. So that's a big arm of our company, is the research and program side. In addition to that, we do consulting with building owners and entire communities, help them with energy planning and delivering energy savings. And we also do local policy and state level policy work. And we are the largest energy efficiency lender in the state of Minnesota. So we do a little bit of everything, with the idea of delivering energy efficiency and savings to Minnesota residents. So to dive right into things, what is an air source heat pump? That's really where we're going to start today. And an air source heat pump is really like an air conditioner, but it can also work in reverse. So what this diagram shows us on the top is a heat pump running in reverse, where it's actually pulling heat from the outside and moving that heat indoors to heat the home. So it delivers that heat through forced air distribution, similar to a furnace, but often through ductless heads that you may have seen, and we'll cover that a little bit later. And then it can also deliver cooling like your typical air conditioner. So in that, it's kind of pulling heat from the inside of the house and putting it outside and bringing cold air in to distribute throughout the home. So what really differentiates this technology is that instead of an air conditioner which can only cool, a heat pump can cool and heat a home. It delivers both of those through forced air distribution. And really, this technology advanced considerably in 2013. Heat pumps have been around for over 20 years, but they haven't worked very well in cold climates because, as you may guess, it's hard to pull heat out of those cold winter environments to then be able to efficiently deliver it for heating your home. So in 2013, that changed a little bit, and now systems are able to deliver heat at temperatures as low as negative 13 degrees. So they're actually able to pull heat out of negative 13 degree air and move that heat inside to heat the home. And that's why it is called a heat pump, because essentially it's pulling heat or pumping heat from one way to another. And that's done through that refrigerant system like your typical air conditioner. So what makes a heat pump cold climate? Really what changed in 2013 was this inverter technology. So they're much more efficient devices or condensers, so they're able to extract heat at these low temperatures, and they're able to deliver that heat into the home at efficient levels. They're able to move heat at -13 and all the way down to -20 degrees. We found in our studies they're actually able to move that heat at those low temperatures. They have other efficient devices like an ECM drive. They also are able to modulate to meet building modes. We'll talk a little bit more about that, but what that means is they can kind of hone in and meet the exact heating load or cooling load for that home. So they're able to modulate and adjust to continuously meet that load for that home. And they're also very quiet in operation, both inside and out. So if you're looking to kind of find or differentiate one air source heat pump from another, and you're interested in finding cold climate heat pumps, here are some of the product specifications to look for. The key is that inverter-driven technology. And then you also want a COP, or coefficient of performance, of 1.75 at 5 degrees. And what that means is the system's able to operate efficiently at 5 degrees, so 1.75 at 5 degrees, or an HSPF above 10 and a SEER above 15. And the Northeast Energy Efficiency Partnership, or NEEP, has put a list together of products that meet these specifications. So if you want to look up a product, they're a really great resource to go find a piece of equipment and if they meet those specifications. So heat pumps come in lots of different shapes and sizes, so I wanted to cover those different ideas and types today, and we'll be talking about those throughout the presentation. But as you can see here, this outdoor unit on the left looks like your typical air conditioner. That is your outdoor air source heat pump with a ducted fuel system. So that's the outdoor unit. On the right is the indoor unit, and it's paired with a condensing propane furnace. So the unit connects to that indoor distribution or the air handler through, by putting the A coil through that system. And with having it be the propane as well, the propane can serve as the backup. And we'll talk about how that backup propane furnace that you see on the right interacts with the heat pump in the outdoor unit that you see on the left. In addition to a ducted flex fuel system, there's also a ducted all-electric system. And this outdoor unit looks a little bit more like what you're seeing when you think about a heat pump that connects to your ductless, except this outdoor unit connects to an indoor air handler that you see here. And that indoor air handler has the A coil from the outdoor unit, but it also has an electric resistance booster heater. So when the heat pump can't meet the full load of the home, that booster heater comes in, and then that hot air is distributed through your typical forced air system with an air handler. So these are the indoor and outdoor units and what they look like for an all-electric system. And then here's your kind of ductless mini split that you may be familiar with heat pumps. You have an outdoor unit that looks similar to that of the one that we just saw with the all-electric system. And then you have this indoor head, as it's typically called. And what that is a kind of single location that's pushing that hot or cool air to meet the heating or cooling load for that space in the home. So there can be multiple heads within a house as well, but here's kind of a picture of a single outdoor unit with a single indoor unit to meet the heating or cooling load in that space, as well as the thermostat for that unit. So that's kind of what heat pumps are and the different types, and we'll actually come back to that with some new construction applications, but I wanted to show you some of the results of our cold climate research. So here's a timeline of our research and how we got to where we are today in 2020. So in 2013 is when that inverter-driven technology was introduced, and shortly after that, NEEP specified this equipment as being cold climate. So we saw this going on, and then in the winter of 2014, we had some propane shortages in Minnesota that many of you will remember, which really drove up the price of heating with propane in our state, made it unaffordable for many people, and a lot of people were kind of going out and getting electric resistance heaters in this time because they couldn't find propane or it was too expensive. And really these events led up to Center for Energy and Environment wanting to do some research on if these cold climate heat pumps could actually deliver heat in Minnesota. So we wanted to field test that and see how they did perform. That research started in 2015, and then we moved into testing out all electric systems in 2017, and our research continues today, which a lot of the newer research started in 2019, where we're looking at optimizing it for single family homes and some multifamily applications, which we'll talk about. So we wanted to see, can these systems work in Minnesota? So they say they're cold climate ready, but can they actually perform? So here's a map of the 8 sites where we installed and tested systems in Minnesota. We wanted a variety of system types and a variety of locations. So you see one system was installed in the Duluth area and then up by Lutsen and Grand Marais on the North Shore. We had a system in western Minnesota and then some around the metro area in Rochester, just to get a variety to see how these systems could work in different outdoor environments and different temperatures. And then we monitored all this equipment to see how it performed. So in addition to a variety of location, we wanted a variety of different manufacturers and system types and sizes. So the green systems are the ducted systems that we looked at. The 4 on the top are the ducted dual fuel systems. So those had a propane furnace as well as the cold climate air source heat pump. The 2 green ones on the bottom were our ducted all electric systems, which we'll talk more about. And then the 2 black ones are the ductless mini split systems that we installed. So this slide really just illustrates the amount of data we were collecting on all these units. You may say, well, you've only really looked at 8 units, but we looked at those 8 units in great detail. So, there are 11 points of measurement. We were collecting 1-second data, or sometimes even finer quality of data for all of these different varieties. So we're looking at the power measurements of the outdoor and indoor units, the fan measurements. We're looking at supply air, return air to see what kind of heat these systems are delivering, the temperature of the conditioned space, and then of course the backup fuel consumption and the weather data to really see how these systems are performing in the field. So we collected a ton of data on these systems to see how they were performing in the field. So this graph kind of summarizes, 4 or 5 years of research into one slide. So I'll slowly kind of walk through this to give you an idea of what we saw from the performance of these systems in the field. And what you'll notice is the horizontal lines around the bottom, those are your traditional HVAC systems. So that dark line right along the 1, that is an electric resistance system, so that's 100% efficiency. The 2 lines below that are your condensing and non-condensing furnaces. So those systems, it doesn't matter what the outdoor air temperature is, those are the efficiency that they operate at. So you'll see that those are below 1. So our y-axis is the coefficient of performance. So 1 is electric resistance, that's 100% efficient, all of the heat going into heating that space. And then below 1 you have your condensing and non-condensing furnace. And then you have the temperature on the x-axis. And I'll start by kind of walking through what this blue line means, which is our all-electric system. So as you can see at these higher temperatures, all the way down to 30 degrees, this system is operating at above 2 COP, so above 200% efficient. So it's pulling that heat from the outside, delivering that heat to the inside of the home at 200% efficiency because it's moving that heat around rather than creating that heat. And as it gets colder and colder, the efficiency of that system goes down, but even at as cold as -10 degrees, that system is still operating at above 100% efficiency. And what's happening with this line and that curve that goes along with it is that electric booster backup that I talked about with that ducted system is coming on to meet part of the heating load of that home. So the heat pump continues to operate and move heat from outside to inside and distribute heat for that home. But at a certain point, you're seeing the electric booster come on, which drives this efficiency lower because that's 100% efficient heat. And that's where you see this kind of flatten out. But that heat pump is still delivering heat at as low as -13 degrees where we recorded here. And then the backup heat, the booster, is meeting some of that load as well. So that's why you see a drop below 1.5 when that booster is coming on. So with the other heat pump system, we're looking at the dual fuel system, which is this maroon line. And as you can see, at these higher temperatures, it's still operating at around 200% efficiency down to between 30 and 40 degrees, but you see a steeper drop off in that efficiency. And that's because at a certain point, the heat pump can't meet the entire heating load of the home. And rather than, that electric booster coming on to meet part of the load, with the dual fuel system, it's a hard switch. So you go from your heat pump operating and meeting 100% of that load to your furnace meeting 100% of that load. And that happened at different temperatures depending on the time of the year and the weather. But as you can see, at about 13 degrees, you're always switching over and operating with just that propane furnace to meet that load. So with this system, it's a steeper drop off because it's a hard switch over between when your heat pump's operating and when your furnace is operating, and they both aren't ever operating at the same time. So what that resulted in from an efficiency level over the winter was your all-electric and ductless systems are producing around 1.9 to 2.1 is your average COP over the entire winter season. That means that they're operating at 200% efficiency compared to electric resistance because they're moving that heat around. They're able to get those extra benefits and deliver a ton of efficiency and savings. With your flex fuel system, it's a little bit lower because of that hard switchover. So the average COP over the winter when we tested was 1.2 to 1.3. You're still getting over 100% efficiency with those systems. It's just a little bit lower with that switchover. So what does that mean from a customer perspective, from a single home perspective? The conclusion of this study was we saw significant savings for these systems compared to propane or electric resistance heating systems. So when comparing a home, which many had, that had a propane furnace when we went in, and then we put in this dual fuel air source heat pump, they were able to get 40% site energy savings, which resulted in 30% savings for homeowner costs. That equates to around $250 to $500 per year, and a slight reduction in the carbon emissions that were put out to heat their home as well. We'll talk a little bit more about that. And then on the all-electric side, since you're going from a house that had electric resistance to this all-electric ducted system, you're really getting all of those benefits. So on average, we saw above a 50% site energy saving, 55% homeowner cost savings, resulting in $500 to $600 per year. So when considering, what systems to put in, really the heat pump was able to perform in our climate, was able to meet a lot of that load, and it was able to deliver a lot of savings compared to just a propane furnace or just electric resistance. So a summary of what that meant is with that ducted dual fuel system, the cold climate heat pump is meeting the home's heating load 84% of the time. So it's meeting that home's heating load for the majority of the winter. That other 16% is when that propane furnace is operating. And what that does is it reduces a homeowner's propane consumption by 64%. For most homes, what that's going to mean is less than 500 gallons of propane used per year. And the huge benefit of that is 500 gallons is typically the size of your propane tank. So a customer can fill up their propane tank when prices are lower during the summer and then know that they won't have to refill their propane tank over the winter because the heat pump is meeting the majority of their heating load. So that was another big benefit for that system. With ductless systems, it's a little more refined on the design for how much of the heating load and savings you will deliver. And that's because it's kind of where you decide to put in those heads and how much of the heating load that system is going to supplement. So as we saw from the efficiency graph, it's still operating at that 1.9 to 2.1 COP on average throughout the winter. And then it's supplementing that heat for wherever you put the head. So if it's in the living room, which used to have electric resistance, you'll see the savings in that area. But the percentage of heating load depends on kind of how many heads you put in and how much of the heating load you plan to meet with that ductless system. So some additional benefits. The ductless systems deliver heating and cooling where and when it's needed. So there's no more cold or hot spots in the house. If you put a head in that area, it's going to deliver and it's going to heat or cool that area to the exact temperature that it's set to. So they're really meant to continuously operate and deliver that exact amount of heating or cooling that you need for that space. So they're really putting in that tempered air exactly what you want at a consistent basis, and they're able to keep that area at the exact temperature that you want. And then when you start looking at these different system types, there's really endless zoning and sizing options for these systems. They go down to very low BTUs in sizing and up to very high, and you can combine ducted and ducted systems together. And there's new kind of variations on that all the time, but it's really endless if you want to put, a ductless head up in an attic area, or you want to have ductwork for the rest of the house. You can do a lot of different things with these systems and know that they're going to heat and cool those spaces. like I said before, they have quiet operation both inside and out. And they can also have indoor air quality and filtration benefits because of that continuous operation, because they really modulate down with that inverter to meet the exact load of the home for that time of day and what the call for heat or cooling is. So next I'm going to talk about some system considerations when looking at choosing or installing an air source heat pump. So keeping it focused on the new construction side here, kind of the main application things to consider when looking at an air source heat pump. And really one thing I wanted to mention is that if you're looking at putting in an efficient air conditioner and just simply defining that as 15 SEER or higher, it likely makes sense to install a heat pump. You may not want to pay the extra cost, which we'll get into next, of the cold climate heat pump. But a heat pump in general has a 15 SEER or higher. It's comparable in price to an air conditioner, and then it can be used to deliver heat at those more moderate temperatures, that 30 to 40 degree range that we saw. So it really makes sense to put a heat pump in all homes if you're thinking about installing or putting in an efficient air conditioner above 15 SEER. It also makes sense if you're not in natural gas territory. So as was made very prevalent in that research table, it can deliver a ton of savings compared to propane heat or electric resistance heat. So if you're ever considering propane or electric resistance because there's no natural gas hookup, you're going to want to recommend a heat pump or install a heat pump for that home. The other time it makes sense is if you're in natural gas territory. From a cost perspective, it's important to look at the cost of heat in that area. So typically it's between 10 or 12 cents a kilowatt hour to heat a home, and at that price, it will be more expensive to heat your home with an air source heat pump compared to a natural gas furnace. But there are a lot of utility rates out there for electrically heated homes, for dual fuel homes. There's off-peak heat rates. So it's important to look at these rate options that are available to you and your customers when building a home, and where it becomes around cost neutral with a natural gas furnace to heat, and this is kind of on the operating cost side, is around 6 cents per kilowatt hour. So if there's an electric heat rate or dual fuel rate where you're building, then it can make sense to put in a heat pump and then have a dual fuel system there. It also makes sense for applications where you don't want to have ductwork, so there may be limited space. You may be doing a renovation or an ADU and it's a smaller energy efficient area. You can put in a ductless mini split if you don't want to put ductwork in. And then if you have customers who are interested in reducing their carbon footprint, so you have an energy efficient home constructed, which we'll get to in our case studies, customer that wants to do on-site solar, then it really makes sense to heat with a heat pump. It provides heating with electricity at the most efficient level that's available to us right now, and can help reduce that carbon footprint down to zero. If they're in Excel territory, they can sign up for WindSource where they're getting all of their electricity from renewables, or if they have on-site solar, it can help supplement the carbon footprint for that home. So when looking at these different applications, I just wanted to touch on the different types again. So, depending on if you're using it to get that dual fuel rate, then you'll want the ducted dual fuel system. If you have someone interested and only wanting to heat with electric because of their carbon footprint, then the ducted electric system likely makes the most sense. But then ductless could also work in those cases, depending on the design of the home and where you can put those heads and how you want to do it. So it's important to consider and know all of the different types and options available to you when it comes to heat pumps and those various applications. It's also important to consider install costs. So we did this study between 2015 and 17 is when we installed a lot of that equipment. And at that point, it was costing around $14,000 per system. And what that is that's the total cost, including the cold climate heat pump and the new air handler or furnace. So since 2015-17 timeframe, costs have gone down quite a bit. This market's grown a little bit. So prices are a little reduced below that. And then looking at just your system type, here's some information reported on pricing. So your typical 3-ton cold climate heat pump costs around $6,000. And then if you're pairing that with the new condensing propane furnace, that's that $3,000. So we're seeing prices more around $10,000 right now compared to the $14,000 during our study. And then just that application type that I looked at, it's around $800 of an incremental cost to go with an energy efficient heat pump compared to an efficient air conditioner at a similar SEER level. But to help with those costs are utility rebate programs. These programs are growing and becoming more robust. As time goes on, utilities are interested in this energy efficient technology and promoting it to the market in Minnesota. So here's some, a synopsis of where these rebates are at right now. They do change quite a bit, but as you can see, Minnesota Power offers as much as $1,000 for a ducted cold climate system. Some utilities like Otter Tail Power do it on a per ton basis. So it's important to look at what those utilities are offering both in terms of rebates and rates when thinking about installing these systems. And to help with some of that, we've developed some resources. So you'll see a Minnesota utility rebate map at this URL. You can go there, you can select your utility, and we have a summary of what their air source heat pump rebate is, and you can link directly to that utility's website from that map. We also have contractor resources and trainings that we're launching to get contractors more familiar with this, and some consumer guidance. Clean energy resource teams or CERTs is always good. So if you're interested in digging in a little deeper on this technology, we provide some resources available to you, and we'll be talking a bit more about it today as well. So with that, I'm going to pass it off to Phil Anderson to talk about single family case studies.
All right, thanks, Isaac. And I'm going to follow up where Isaac left off. I'm going to go over some single-family case studies of air source heat pumps we've seen over the last few years for new homes we've worked on. So first ones we have is an accessory dwelling unit, or an ADU. It's a smaller home detached from a bigger house in the city. A small duplex that's side-by-side, slab-on-grade, a smaller retirement home, and then a larger family home. We'll show some examples of there. First, this accessory dwelling unit, the ADU, it's about 650 square feet. It's one bed, one bath ADU built above the garage in the back of the city lot. The system is a 2.5 ton. It's got 2 wall unit heads in the unit and then one head in the garage below. So the client wanted some heat in their garage partially, so it's a little oversized for that than just the rest of the apartment or ADU. Total install cost for this ran about $8,300 plus electrical cost to install. So really not too bad and pretty close to what a forced air furnace and higher efficiency air conditioner might be. And some client feedback on this one. Estimated costs for heating of about $500 to $600 from October through April. And then similar feedback is about remotes. So usually in these heat pumps, sometimes you have remotes or sometimes you have wall control. They're complaining about the remotes for the heads being finicky and are not very user-friendly. They were looking at replacing those with a hardwired thermostat just to kind of make that a little easier for controls. And then they also think the sizing for the code insulated building for heating led to some oversizing for the AC. So they've had some dehumidification issues. Along those notes, these air conditionings or mini splits are not meant to dehumidify. Some of them have dehumidification cycles on them, but in general, you'd still want a dehumidifier to kind of solve some of those problems. You shouldn't really rely on this for that to solve all your dehumidification needs. And they also went with an electric baseboard for the backup heat. So that was only needed once during the polar vortex winter. So definitely this thing was performing well, it looks like, and provided a lot of good, efficient heat. And on to the next one, we got a small duplex here. As you can see in the bottom left picture here, that's side-by-side, slab on grade, one bed, one bath on each side. And then this one also had exterior insulation, I believe it zip sheeting. It's about an R5 or 6 there. And it went through the DOE Zero Energy Ready Home rating program. Got a HERS score of 43 on each side. The sizing is about 530 square foot per side. And then the system is a 1 outdoor unit, 1 ton per side, ducted system integrated with an HRV. So the ducted is like a mini duct system here, kind of a low flow system, very efficient, very small. It's tucked in a little mechanical closet next to the water heater, and then ducted to all the rooms for heat. And then for backup heat, they had 2 small wall-mounted electric heaters. So those kick on. It's a certain set point if this can't keep up. So It's a great size option for a smaller place like this. There's just no furnace on the market that's natural gas that could provide this kind of heat, but then it's a lot more efficient than doing like a baseboard, electric baseboard, or something like that. So it's working good so far, but yeah, it's a good solution again for a small load home like this. And next here we have a smaller retirement home. So the description here is it's all electric, super insulated, passive house designed. They put 19,000 pounds of its cellulose insulation. That's a huge amount of like a semi-load full insulation there. It's very airtight, slab on grade. They had a 10 kW solar array on site. The HERS is 34 without solar, and then the HERS -6 with the solar. So they planned a little bigger solar array to provide for a future electric car on that one. The size of the house is about 2,000 square feet. And the system was 2 outdoor units, 2 heads, 1 up and 1 down. So 1 head per system. That's sometimes more cost effective and just kind of easier to set up and control versus 1 outdoor unit that has 2 heads. So they went with that route there, and they have electric off-peak backup heaters. This is kind of a little rural area here, so they had off-peak through their utility for backup. And then they used a sealed combustion wood stove as well for backup heat. Some feedback from them. They've been using it about 5 years now. No complaints on the heat pumps. Here's a picture of the mini split heads in the unit, and then or in the house. And then here's the stove they have. It's a sealed combustion. And then right next to that would be the brick heaters. That's the off-peak where it's charging during off-peak hours there and producing heat for the house. So use that off-peak heaters for much of the load, and the wood stove as well. It's got passive solar design, which keeps the home quite warm during the day, and they really don't have much need for any heat at all on sunny days. They got very efficient triple pane windows that are shaded properly and allow the most solar heat gain during the winter months. So really good design, goes a long ways there. And then when the heat pump's on, it typically uses less than 1,000 watts. It's drawing, so very low load, only puts out what's needed. It's back to the inverter that Isaac was talking about, where it kind of just modulates what's actually needed. The homeowner measured 0 degrees on a 0 degree day. The heat coming out of that head on the inside was 85 degree air. So it's working incredibly well still on a 0 degree day, bringing heat inside. And these guys, so the clients here, it's like 9 of 12 months the utility pays them. So they really have minimal bills in this house here. And here's another example of a kind of a custom larger home. It's an all-electric, super insulated, airtight, I believe SIP panels throughout the home. The air tightness was 0.12 ASH50, which is incredibly tight. We're 110 CFM. I mean, it's definitely one of the tightest houses I've ever tested. Yeah, just very well built, very efficient build here for this, very efficient windows too. The HERS is a 36 before solar. It's very large though, 5,000 square feet, 3 levels, and then there'll be a big solar array up on top of the roof there. The system here is a 1 outdoor 3-ton and then 1 indoor unit, fully ducted air handler with a built-in electric resistance backup heat. So it's rated for about 38,000 BTU of heat at 5 degrees. So it's a very small system or heat amount needed for this huge house. That's normally you'd probably see a 60 to 80,000 BTU furnace in a house this size that's built like code standards. So definitely got that load really down there, so you could put this nice heat pump in. Some feedback from the owner and builder. Owners have reported that heating and cooling have been working well, getting even temps throughout the home. This builder in particular has built several all-electric homes, and he really liked this fully ducted system in this one, and that there's a single inside unit and a single outside unit, so just a lot less to maintain, a lot less to deal with if there's issues. Very accessible to everyone that's you can service it or work on it or change filters. And he'd had previous disappointments with callbacks and service issues, and then finding good techs locally to fix other ones. So this one he's been really pleased with, and actually just finished another house recently with the same setup, and that one's been working well also. But yeah, as far as controls go, back to that, it's been kind of a general theme sometimes with the some of the controls plumbing systems are pretty poor. So this one, he's definitely recommending just a simple programmable thermostat that is easy to use, that the clients understand, and just something to avoid callbacks on. As far as maintenance, just checking the filters. That's the key, that callback he's been seeing. And then another key feature of this system here, on the air handler here above is a built-in electric strip heaters. There's 2 stages of it. So I believe it's a 10,000 BTU, 5,000 separated into 5,000. So it can call for backup heat as needed in little increments, not just a full on or off. So it really helps keep that efficiency up there and keeps the bills low for the house. All right, now changing gears a little bit, energy ratings and certifications. So we have 4 common energy rating types. And energy ratings are, add additional energy efficiency certifications. They can help achieve an efficient home with lower load in the heat and cool. So following some of these will really kind of help get your load down, and design the house to follow these parameters will allow you to put some of these heat pump systems we just talked about in. So it's a very good path to follow if you're looking for some kind of different outside certifications. So we'll go over the RESNET HERS rating. So all these other certifications I'll talk about are based on or go through the HERS index. So it's just a modeling tool with site visits for the homes, and then you can add on to there, you can add on Energy Star new homes, which is going to step up from a HERS rating where you're going, HERS rating doing any code home. Energy Star homes a little above code. Then we'll get into zero energy ready homes from the Department of Energy. That's even further above Energy Star as far as energy efficiency requirements, and then up to the FIA standard, which is a Passive House Institute of the U.S. So that's even further, a lot more modeling, a lot more checks and balances, and just a overall more energy efficient designed home comes out of that. So one thing I will say about all these certifications and ratings, if you're going to pursue any of these, it's good to bring a rater into the process early during the design to do a projected rating and kind of help sure all the mandatory requirements are met, and then also that you'll achieve that HERS rating you're shooting for, or the certification you're shooting for. So that's very important to note that. So the RESNET HERS index here is on the right side. You can see the chart. People have probably seen this before. So basically a home that's zero energy uses zero as a score of 0, and then the reference home we'll talk about in a minute, that's 100, but it can be anywhere in that. It can be used on new and existing homes. Today we're just going to talk about new homes here. So for the visits, we do about 1 to 3 visits to the home during construction. So typically it'd be a framing inspection, and then an insulation inspection or pre-drywall inspection, just kind of grade the insulation, check all the air leaks, make sure everything's sealed up, provide any advice there. And then we do a final testing where the blower door duct testing, and then document all the appliances for the energy model. And then the home goes through a modeling to get the HERS index. So we're typically using REM rate or Ecotrope are the 2 kind of big ones being used in Minnesota right now. And what this HERS index does is just kind of a way to compare homes' energy usage between other homes. So some builders kind of compete based on what was your HERS score, what's I'm building better than the guy next door. So it's just a good tool to kind of see where your home falls, and it kind of helps just kind of see that scaling of your energy usage for that particular home. But the HERS index of 100 is a reference home, which is equivalent to a home built to the 2004 IECC. Again, the HERS index 0 uses no energy. A typical home built today in Minnesota, just kind of code average home would be anywhere between 45 to 60. So that'd be something you'd kind of see on the markets. Definitely go well below there, like I showed a couple of previous examples, or even above 60, depending on the townhomes and some slab on grades might score a little higher, I guess. Of the 7,200 rated last year in 2019, the average score was 50 in Minnesota. So that's quite good scores here, and I'll show you the next slide here, some other states and where we kind of fell there. So for the last year, we were like 4th in the nation. So Minnesota came in at HERS 50, with just Vermont, Hawaii, and South Dakota, all pretty low populations. So we definitely, for the amount of homes being built, we have the lowest score of others around us. And the incentives, we do have utility incentives that kind of drive some of this, but that's a pretty good score for Minnesota. That just kind of shows you where we're at, just kind of with our homes that are currently being rated. And Energy Star New Homes, it's another certification program. It's a very common label. Most people have seen the Energy Star label, whether it's on appliances or other stuff. It's an EPA-sponsored new home program, typically using 15 to 30% less energy. And it's certified rater, makes 2 to 3 visits to check this home out. Again, it's the framing, installation, and then the final testing and other tests if needed in between. And then the builder and HVAC contractor have to go through a training for the program. So Energy Star puts on a training for this, and the HVAC contractor has to go through one of 2 providers to do a training as well for any ducted HVAC systems. And then the HVAC contractor is also required to properly size the system. So you have people doing good checks and balances on the manual J, D, and S for all the sizing of the equipment, the duct systems, the airflows, everything like that is checked over a lot more, and it's designed well. That's kind of a key takeaway from this program. It's helps a lot, and then we also do a lot of testing on the end, on the energy rating side, to ensure that these systems are working better. The 3 key checklists that are followed: the thermal enclosure checklist. That's something as raters we would go out and check all these little check boxes for every kind of air leak, bypass, just design, making sure the insulation air barriers are lined up, checking HVAC systems. And the HVAC could hire a designer, and then also they can fill out a quality installation to complete those checklists, so they can have a separate party design the system, and then just verifying at the end with a quality installation checklist that everything's working as designed. And then there's a water management checklist as well that builders need to follow, and that's kind of really drives home keeping water out of buildings and just making sure everything's gonna buildings can be there for a long time. So a little more durability in that as well. And again, like I mentioned, Energy Star is great brand recognition. It's a good way to get builders to set themselves apart from other builders. And there's definitely some builders we work with that are request this and have more leads from home buyers with this, going through this program. So and you can find more information there on that website. Next, we're going on to DOE Zero Energy Ready Homes. So that's the Department of Energy's program they started several years back now. It follows the Energy Star New Homes checklist, so you kind of have to do that as your base tier to get into this program, and they're typically about 40 to 50% more efficient than new homes, than just like a code home. Energy Star qualified appliances and fixtures have to go into the home. You have to use a higher performance windows, that's mandatory, so it's a little better than our Minnesota code window needs to go in. And then you have to meet the ICC 2015 code levels for installation. So in Minnesota right now, we're so 2012 with amendments for our code. It's a little more robust installation package you have to put into the home to meet this program. And then ductwork's required also to be inside the envelope, which it is in Minnesota, but you can test it to get around that, but it's still just a best practice, and it's a good requirement to have all the heat and cool air inside that thermal boundary of the house. And then also hot water distribution systems is something we test, and it should be designed into the home. So that's just about getting that hot water system to provide the hot water in a short amount of time with as least amount of loss as possible. So that could be done by design, or it could be done through a smart pump that has like a switch in a bathroom or the furthest fixtures to kind of make sure that hot water is delivered quickly without wasting water. The indoor air quality certification program through the EPA, the Indoor Plus has to be followed, and that's more just indoor air checks on like low VOCs, radon, other stuff that's just trying to keep that indoor environment healthy throughout the build construction process and all the materials going in that home. And then you have to make that home PV ready if the climate is significant solar insolation. So depending on where the lot is, there's a little chart you can look up on PV watts from NREL that kind of shows where, which house has to, would have to have that built into it. And it's, I think, just good practice anyways to put that in no matter where you are. Just, in the future, solar might come down so much where everyone wants it. It's just a lot easier to run, lines in a pipe right now just for future of solar. And you can find more info on that website there. And now we're on the FIA certification. That's a little even step up from all these. Last 2 I talked about. It's got greater shell insulation levels, tighter construction. It's got really, only one of these programs that has like a strict, like you have to hit this level tightness to qualify. And then also continuous ventilation is very key. When you get to these kind of thresholds of tightness, you really need a robust ventilation system. We're going to talk more about air sealing later, but you really need a lot of fresh air. The more the tighter your construction is and tighter the building is, that continuous ventilation just really becomes a very, very key component of the process. And the costs go up in that amount, where you're spending money is probably going to go up in that area there. But it also follows and earns the Energy Star Indoor Air Plus and DOE Zero Energy Ready Home. So it goes through all those certifications as well. So you have to follow all that we just talked about. And then the home would also be modeled by the HERS rating software for those programs. And then also you'd have a certified passive house consultant or a CPHC that does the WUFI hygrothermal modeling on that house, and that's kind of leads that process through with FIAS to get the home certified. So if you're thinking about doing this, we always recommend, again, early checks in with FIAS and your rater and your CPHC to make sure this house or building you're going to build is going to meet these requirements. And there's more info you can find there at fias.org. And here's a good slide. They've kind of put together to kind of show the different programs and where they kind of stack up against one another. So here in Minnesota right now for code, we're kind of following this IACC 2012. And that's, our code's a little different. We don't have like exterior insulation and some basement insulation is a little different, but we're roughly around that right now. And then we, Energy Star, we're following Energy Star version 3.1 here. So what you have here is you got the HVAC quality installation, you have the water management, and you have the independent verification of the ratings. That kind of steps you up from just a standard code home. And then to get to Zero Energy Ready, you eliminate those ducts or put those ducts in the conditioned space of the home. You follow the EPA's Indoor Air Plus checklist, and then you have efficient water distribution and appliances. And then also you have to make it solar ready depending on where you are. Then with FIAS, it adds the mandatory balanced ventilation, which is code in Minnesota, so that's not really an add-on. But again, like I was saying, houses are going to be tighter, so you're definitely going to want a better, more robust system that's probably called for by just our basic code here in Minnesota. Now we're going to move on to multifamily. So this is a shift from the single family. We're going to kind of talk about a bunch of different things on multifamily projects. So we'll go through some certifications, air sealing, ventilation, and then we'll wrap it up with some heating and cooling and get into some different options there, as well as the air source heat pumps. So for multifamily energy ratings and certifications, there's, again, those three common energy certification types. You have the Energy Star Multifamily New Construction, which is a new program, and then we have the Department of Energy Ready Homes, and then the FIAS. So these programs have, again, good mandatory energy efficiency details designed into them. They can kind of help ensure the building achieves energy efficiency above that code minimum. Performing that early energy modeling will help determine which items are cost effective and which ones will help you meet your efficiency goals. And then if you're pursuing one of these programs, same as single family, make sure you incorporate that energy rater early in the process. It's just way too difficult to meet the goals and any program requirements, kind of jump in the middle or bring someone on late or don't let the trades or other people know that you're trying to achieve a certain certification. So the Energy Stars, so we get the new multifamily new construction program, which is a new one. I'll just briefly talk about this today. There's much more information on their website, but in the past it was they've combined the two programs. There was a energy efficient or Energy Star new construction, which was, like I talked about, that was mostly used in single family up to 3-story. And then you can take another pathway when you go above 3-story called the multifamily high-rise program for Energy Star. So right now you can pursue this path, which is kind of a combination of those two programs. And then this one will be required starting July 1st, 2021 as of today. That's their rollout date for that. And again, there's 3 paths. You have the ERI path, which is the Energy Rating Index path, which is kind of a performance-based path. You have the ASHP modeling path, which is pretty common in the multifamily high-rise right now. Then you have the prescriptive path where you meet all the check boxes, then you can meet the requirements for that. For checklists, and then the multifamily workbook to complete, you have the similar ones for what's in single family, and the old multifamily workbook is kind of condensed now into one. And then for common spaces, they're all addressed now in buildings. So that's something that's a little different for the lower, smaller buildings that those common spaces haven't really been addressed in the past through this program. Now they're going to be picked up, and there's going to be some key items that have to be done there. And then you can find more at their website, which I recommend checking since they're going through a lot of changes right now if you have more questions on that. Next, we have the zero energy ready homes for multifamily. So that, again, very similar to the single family, and currently can go up to 5 stories buildings through this program. Similar to the single family for basic requirements, the indoor plus still needs to be followed. There's more at their website, and they currently are updating this program to more closely follow the Energy Star multifamily new construction better. So it'll be a little easier to go through that program with that as well. And then the FIAS is as well goes in multifamily. I think there's probably even more traction going through this program in the multifamily realm than there is in the single family. Again, this program requires greater shell insulation levels, so you're definitely well above code and above DOE zero energy ready homes. The tighter construction is definitely still mandatory. So if you're doing like an apartment, you have to have a certain threshold for that room or units, as well as the whole building will have to be retested as well. So that's kind of something that our programs don't require as of now, is that blower door for that whole building. So this is something that's it makes you really pay attention to the whole air tightness of the whole building throughout construction. And again, continuous ventilation is key here. It's got similar requirements to the single family, and it's likely the most cost effective due to that scale of build. So with multifamily, it's just a lot more cost effective to replicate this. It's one shell, less kind of square footage per unit cost, I guess you'd have. So we're seeing a lot more traction in this program. A lot of buildings being built in Chicago and on the East Coast, and they're really showing it can be done at larger scale, like this multifamily stuff. So definitely a lot of traction there in this program. And then also, again, follows that Energy Star, Indoor Plus, and Zero Energy Ready home certifications. And then it's also modeled through the HERS rating software, and then a certified Passive House consultant does that WUFI modeling for this as well. And then again, I'd recommend checking their website as they're continually updating and coming out with more information for this program too. All right, so we're gonna get into some multifamily air sealing. So very big topic, I guess, and just really wanted to kind of highlight this in this whole presentation. Just to achieve these kind of more efficient energy heating systems or air source heat pumps, you really do need to have a good plan in place to get these buildings tighter. So why do we air seal? So we're doing a lot of it's just for energy efficiency, to keep that heated and cooled air in that house. You're not constantly conditioning the outside air. You get comfort there. You have less drafts. You have more stable air, kind of more even temperature throughout the day. So you get less complaints, better comfort. You have noise reduction. So especially multifamily with those shared walls, tightening those up so there's no air movement between them. That also reduces the noise going through them. And then less odor transfer between the units. So that's very key as well. So if a smoker living on one side, or someone who cooks a lot of foods that smell, or whatever the smells may be, come from unit to unit, you just don't want that to transfer between. Talking to builders, it definitely leads to a lot of their callbacks down the road. And once we've worked with builders on tightening up these common walls and corridor walls, they definitely are getting less complaints. They're really understanding and really trying to achieve that, because that seems to be quite a few of their complaints after the build is complete. And how to achieve that airtight buildings and apartments and units. So we recommend a good detailed air barrier drawn on the plans for the unit and the building. So each unit should have its own kind of outline of where that air barrier is going to be. What is it? What are you using? What material? How does it line up with the rest of the components? And then the whole building as well. So you want to really detail that out, and just there might be a couple air barriers, but you just want to make sure that they are lined up with that insulation and drawn clearly, so there's no question from any of the trades. I've been to many job sites where the trades are questioning where it is, what should it be, and it's just it should be coming down pretty clearly to them that this is where it is and this is what it should be. And the key areas, you just really want to go zoom in on those details in the plans as well. So if there are little tricky spots around windows or bump outs or other tricky components of that building, really just kind of detail that out for them. And really get the project manager and then all the trades on board early. That's definitely a lot of kind of disagreements or fighting down the road, or change orders happens from people that just don't understand what you're trying to do for a building, trying to get that tight building, tight units. So just really getting everyone on board, explain to them the details and how important this is to you through that. And getting a third-party visual checks on it. So that's something that can really help before the drywall is put up. Just really get someone to do a visual, checking those units, just make sure that they're, they are following the standard that you want, and it's getting overlooked and just covered up, and the next thing you know, you have callbacks due to air leaks in different spots. So and then we recommend a blower door testing during construction. So as soon as you get that drywall up, or some builders we work with, they'll call us in for a blower door test as soon as they get that first unit air sealed or enough for that test. So just getting that drywall up, and then maybe a coat of mud, and just run a quick test, seal off whatever you can else you can't with tape at that time. Just gotta see where you're at, make sure you're coming in where you need to be to pass whatever goals you're shooting for. All right, so some examples I'll go through here, some common issues and some solutions. So we got electrical, plumbing, common walls, the insulation, the windows, and then some airtight gypsum on the walls. So for electrical, these are definitely something that can be spec'd out for buildings, and I think really should be. It's a lot of different holes that are caused by electrical penetrations and the boxes, and there's good and bad ones to call for and spec in different areas. So just making sure that those are detailed out. So this top left one, you have the gasketed box, was not air sealed very well with the putty. So that putty is very loose, and that can kind of allow air to go around that, through that. There's certain fire restrictions to follow there, but just making sure that that also air seals as well. And then also on that box too, just there's a little gasket you can kind of see there, that little ring, that mud ring there. You can put a good bead of air sealant around that when you hang that drywall too, and that'll really seal up that box too. But also the wiring penetrations themselves is a good spot to hit. And then next, to the right of that, we get the wiring not sealed. So here's a very common one. So we see a lot where the wires are punched through the box, not being sealed on the inside either. So usually if you have your fire protection on the outside, you can do a little spray foam or other caulking or sealant there on the inside of the box. A lot of times what we see happen here is this electrician comes by at the end and just rips those wires out to put the outlet in or the switch in, and breaks that seal. So you really want something robust there, and then even just talk to the electrician like, hey, these are air sealed, don't pull these too hard, and just kind of get that that seal kept intact. Then low voltage boxes, we see a lot of these are done poorly as well. So it could be like a thermostat, could be a cable, could be data cables running through here, and there's just they just maybe don't make good boxes, or there's just not a good box being installed by them. And a lot of times we find these just open boxes that's just a faceplate holder, which a lot of air would move through that as well then. And so they're just wiring penetrations not sealed. So this one is particular to the outside of the building cavity. So making sure that someone follows along and gets all those holes drilled to the outside of the apartment sealed up good. So it can be an electrician there. And also the other wiring penetrations to pay attention should be through the bands and other joist spaces where those wires are going through. And here's a box to a corridor. So again, you want no seal here at the wires, but then getting a good seal of that manus or sealant around that box when that drywall goes on really helps provide a good seal for the box, then also the wire penetrations too. So that really will help seal up that unit very well there. And next on to plumbing here, we've got some details of the top left here of the common walls, and get plumbing here running for like a kitchen on a common wall there. So after this drywall is installed, really making sure that they pay attention to air sealing around those vent pipes or drain pipes, then also the water lines. And then even in those common walls on the floor there, just anything that goes up and down, make sure that's really sealed well with a good fire caulk or something that's going to stop air as well. So that's a very key important detail there. And then here in this top right picture, you have we want to have good, robust air sealing these plumbing vents. So many times we've been to job sites and we'll see the plumbing vents have been disturbed by people working on floors below it or other trades, who knows, whenever they first might put this fire sealant up top there, that gets disturbed, and then you got an air leak there. So really pay attention to that, making sure everyone understands not, you move this pipe around, it's going to break that seal. So really trying to, either check that right before the drywall is hung again, make sure it's sealed properly, or just putting a little more robust sealant up there. Another thing we've been seeing sometimes is get a party wall, so or a plumbing wall. You have into like a common space or corridor wall here, then the plumbing wall. This particular project, this wasn't detailed out as to air seal this common, this plumbing wall behind here. That blue rock was not ever detailed as an air barrier, so we got there and a lot of air leakage coming from the sides and all around it. And then once they put the next layer of drywall on, none of these boxes or gaskets were sealed, so it just didn't really perform very well. You had air coming in from all around this whole kind of wall there. So that's not really something to back to that old line up that air barrier, making sure everything's drawn on the plan, showing everyone where it is, where you want to continue it. So making sure that's done at that level as well. And I guess in this case, it was the framer putting that wall up, so it's just a different trade doing something different they're not used to doing. Another big checklist item on the Energy Star checklist would be a solid air barrier behind the tub and that connects to walls. So getting something solid in there, whether it's a gypsum product or a cement board, something like that, to kind of really seal that up, or it could be a closed cell foam, something that's just going to make that a good solid air barrier behind that tub. So a lot of times we're just getting air leaks from underneath these tubs that come from the outside wall or from a common wall or a corridor wall. Just get that sealed up before that tub is placed in, or speccing that out of the plan so that gets done ahead of time is key. And it's got some common wall air sealing. So here at the top right picture, we've got some rock wall between the double studs. So that acts as a fire barrier there. It's been approved for that. So you'd have to stuff something in there. We recommend a rock wall that holds up pretty good. And then for air, we've had code officials allow foaming this rock wool above that. So you can come along with a bead of sealant there, seal that whole 1-inch gap, whatever it is, between the double wall to stop airflow there as well. So that's one way to treat that wall there. Then up here at the top right, we have all the penetrations and holes between units. So a lot of times up in this band between units, we'll see huge gas lines or electrical or other plumbing chases punctured through there, not sealed up before that drywall, before the installation contractor comes in. So it's really key to, prohibit that air from, transferring between those and getting those sealed. So every trade should be on board and should understand that every hole they punch in anything needs to be sealed up properly for air as well as fire. And then down at the bottom right, we have just making sure there's a good air seal where that common wall meets the exterior there. So in this case, they used a 2-part closed cell foam on that common wall or party wall there, and that gap. Sometimes we've seen just, if you're doing bat and poly, you can just run the poly between there. Sometimes they'll have like a 2x10 or 2x12 on edge at that space, just making sure it gets good air seal then with a caulking or something. And on to insulation and windows. So insulation, it's always good to have a third party and ensure a good install. So, we're checking the, bats, make sure those are installed properly and air sealed okay. But then also spray foam. It's only as good as it's applied. So here, separation of spray foam. This could have been, from a cold day, too cold a substrate that wouldn't stick to it, or possibly the mix was bad on the truck, so they just didn't get a good seal, and this insulation is just really not doing anything. It's pulled away from the wood, it's pulled away from the outside. It's just not doing much there. Another thing would be this right there, that little gap you can see here in between the two studs there. And sometimes this could be multiple studs on a taller building. Here you can see daylight right there, just kind of foamed here, kind of sealant there, not a really good thick bead to stop that. So there's really a big gap there in this wall assembly. So you might have good insulation values on the in this cavities, but it's just not showing up here in between the wall assembly there. So you really want to pay attention to that and get those all sealed in as well. And then back to just the insulation is in general, it's good to have exterior insulation. When you do have a lot of just studs in a row, sometimes we'll get to these bigger multifamily projects and see 8, 10 studs in a row, and no insulation on the outside. That's really a big thermal break. It's really something that should be detailed out to get better insulation values on those assemblies that have just a sheer volume of wood on the outside walls there. Let's see, the windows. So we always recommend a mock-up window be built. So it's a good way to kind of make sure everything's sealed for water and air. Get that manufacturer involved, get the tradespeople involved, just kind of go through what you want, what details you're looking at to seal that window up. Just really kind of helps the whole build. So if you're going to put in hundreds of windows in this one building, you can probably get a manufacturer that help you kind of go through that, and make sure that's detailed right, and everyone that's installing it or working on it's going to put it in properly so you don't have failures later. As far as the air sealing of them, additionally, we definitely recommend like a backer rod and caulk for better air seal than just one, just the can foam there. So, can foam does okay, but sometimes it's just based on temperature, based on the mix, it might not seal up very good. So, a good backer rod with caulk is a better air sealer than just can foam. And lastly, on the air tightness or air sealing part of the multifamily, I want to talk about some airtight gypsum walls. So how to seal with gypboard to make the tight wall assembly. So this is a air seal in the perimeter of that gypsum with sealant. So typically you're having 2 layers of sheetrock on that common wall, but you'd be hanging the ceiling first, put up 1 layer of that common wall or corridor wall, put a thick bead of sealant in that corner around the perimeter of that, and then put your next piece of rock wall or drywall on the board there to kind of seal that up around the perimeter. So staggering those sheets of drywall and then putting that sealant around the perimeter is definitely going to get a good seal of that wall, make that gypsum board just a really airtight assembly. So again, it's just on the common walls, party walls, corridor walls with caulking, then also any interior walls. So we see that missed a lot. So here's a common interior wall. So you have all kinds of electrical penetrations going up. Looks like they're sealed well there. But again, you're not using airtight boxes. And the gaps or leaks we're seeing here is it's pulling between this gap in the drywall and that framing there. So just trying to get that framing gap sealed up a little better with sealant before you hang that drywall in this interior one really can help reduce that air tightness or reduce the air leakage in each unit, provide a better performing unit there. So something to pay attention there as well. And then again, you do all sides, the tops and the bottoms of this drywall perimeter on each wall. And then it's good to have this detailed on the plans and specs. So go through this with the trades on site. We do this a lot, just training these trades on site before they start hanging it, just how to do this detail, how to get it done right, and then just doing some spot checks by the whoever's a construction manager on site, just making sure they're getting that. And then, like I said, doing floor door testing early on a unit to just kind of verify they're hitting those goals you want to hit. So one other option we've seen done before is poly on one side of the interior walls. It works and it can provide a tight air barrier there and eliminate some of the sealing, but it's definitely been talking to tradespeople out there doing both ways. They prefer the top one here. We're doing the sealed drywall. The poly just gets kind of confusing. Where do you lay it? Which side of the wall assembly? You really don't want to put it on both sides. If you have moisture ever trapped in there, that could lead to some moisture issues or rotting or mold. So just one side would be ideal if you're going to do that. But I'd recommend just a sealed gypsum board for as a good air barrier to make these units nice and tight. And now into some multifamily ventilation. So why do we want to ventilate houses or apartments? So it's mostly to remove pollutants and provide fresh air. Some options we have are spot ventilation. So we've got kitchen hoods like here, and then we've got bathroom fans like this. And we're looking at continuous ventilation as well. So that's a different kind of you want to have your spot ventilations, get rid of your pollutants from the kitchen and bathroom, but then you also want some kind of continuous fresh air brought into that apartment unit. So with that, you can do an exhaust system with one of these fans can be rated for continuous use, either a kitchen or bath fan, and then you can have some makeup air pulled in. It's kind of more bare bones approach to it, or even better yet, you could do a heat recovery with an ERV or an HRV. So best options here are balanced whole building ERVs. I'll show an example of building a little bit in a case study we'll go over, but that's about a huge room that machine took up for a 59 unit apartment building, but definitely the best, easiest to service, change filters and maintain it, being away from the units. The one drawback of this type of system is the huge upfront cost of the box itself, but then also to run that ductwork to each unit is going to be quite a large cost up front. Next best option would be in-unit ERVs. So they make really tiny ones now, maybe 1.5 feet, 18 inches, 20 inches by cube. Really small. You can tuck them into mechanical closets pretty easily. They even have some smaller ones that are about 8 inches thick by like 20 by 20 or so. So they're really have come out with some really good options now, and ones that will serve our Minnesota climate. So you really want one that's rated to go to that below 0 degrees temperature setting for those. I guess with the ERV and the HRVs in units, it's a little lower cost than the central ERV HRV, but it's going to be increased maintenance on it, because it's going to be more units throughout the building. So you have one per apartment to check, which, again, if you're already having someone in there change the furnace filter every month or two, just a quick little check on this is one more thing to do, but it can be done, but it's a little more time involved involved with that. And a step now into multifamily heating and cooling. So there's many options out there in the market. We're seeing a lot of packaged units in unit systems. There are higher efficiency models now with condensing gas units available. And then problems we're seeing with a lot of these are they're just oversized for the space. Buildings have become more efficient, they're tighter. And you're trying to move in all the CFM that's needed to go through this air exchanger, the heat exchanger, and the coil, the coolies. It's heat and cool, and it's just really hard to do with a system this size. So bigger buildings, we're getting essential boilers and chillers, and then also heat pumps can be tied into those, or standalone heat pumps. And then fuel types, we've got gas appliances. You always want to try to go with a 90% AFUE. Most of them are over 95, 96% now. Versus the standard efficiency of 80% AFUE. So we're seeing a lot of package units still at that 80% level. It's really not that much more to go up to the 90%. That just jump in efficiency can really provide some good savings for that tenant who's going to live in that apartment later. So then as far as electric, you have heat pumps, which can be in the 150 to 300% efficiency range. And then you have resistance heat, which is only 100% efficient. It sounds good, but the cost of electricity is so high in Minnesota that it is going to cost whoever lives in that apartment or condo or whatever you're building, it's going to cost them a lot more just to have electric resistance there. So if you're going to go electric route, heat pumps are a good option, and then we'll kind of get into sizing options next on those too. So kind of our overview here of some heat pumps, our mechanical systems and available metrics here. So these cold climate heat pumps, they're rated for -13 to -20 degrees. And we've measured them down to -25, as Isaac mentioned earlier. You have your ducted versus your ductless type, and then you have your zoning and sizing options, which can be just endless at this point for what and where goes where, what heat to what room, what cooling to what room. And you have the VRF systems, or the variable refrigerant flow, which allows for simultaneous heating and cooling. And all these, this inverter type are very quiet operation inside and out. So you're not going to have that old loud air conditioner outside that you always hear. It's just a lot quieter systems with the variable speed and the more efficient motors installed now. So here's some different options here for the different distribution of the heat and cool inside. So you have the ductless versus the ducted here. So on the top left, you have your ductless, kind of your standard wall unit cassette, and that's wall unit. Those range in BTU outputs from 6,000 up to 36,000, depending on the manufacturer. So it's a lot of different range of heating output through those systems. Then other ones that people don't see much, but are very nice, can fit in different spaces quite well as a floor unit. So it's kind of mounted on a wall or on the floor, kind of like a radiator would be. Those range in the 9 to 18,000 BTUs of heat output there. And then you have these ceiling cassettes, which are can be mounted right in the ceiling, kind of looks like an exhaust fan or a little bigger vent from a ceiling. With just good flow there, and those can put out anywhere from 7 to 18,000 BTUs as well. And then down below here we've got the ducted setups here. So we have got these are called ducted slim ducts, really small duct that can be up a little softened in the ceiling, and then you can add a little additional ducting to that. And those range from like 7 to 24,000 BTUs. Here's another example of one that's a little bigger setup, kind of like I showed in that similar to the one I showed in that side-by-side duplex earlier. So there's a ducted setup with a smaller air handler here delivering just one floor of a house. So you can zone these systems too. You can have one per floor to kind of get that BTUs there. Again, you're talking 7 to 24,000 BTUs of range there. So if you can get 24,000 BTUs on the floor of a house, that could easily solve that for that air handling unit there. And then on the far right, you get back that bigger ducted system like we saw. That's those go up to 12 to 42,000 BTUs of heat. So a lot of heat put out by those systems. It can really take over a whole house as needed, as we showed earlier in one of our examples. So the ideal uses of the air source heat pumps. So the commercial VRF systems allows for very few outdoor units to serve the entire building. They're a good solution to a bigger building. When you want to really go for an air source heat pump, and then the ability to provide varying size of loads to different apartments throughout the day. So you can, example would be you can cool on a south facing upper level, and then you can simultaneously heat on a lower level of a north unit. So these kind of moderate days or maybe hot upstairs and cool downstairs. You can, you're essentially swapping the heat from one side to the other side of the building. Then these advanced controls allow for building management to control and monitor individual apartment settings, so they can really dial it in. They can see, set ranges of what the heating and cooling could be, and kind of monitor what that apartment's using as well. And it can also be integrated with the ventilation system to provide fresh air to all the units with central ERVs. So I'll get into a case study in a minute that goes over that, but it's definitely possible to tie in ERVs to this system. Then, the small size is going to eliminate a mechanical room in the unit. So a lot of these bigger packaged units you'll see in the apartments now, they need a 4 foot by 4 foot mechanical room or more just to serve that for the heating system. These can be easily dropped into little chaseways, drop soffits, stuff like that you wouldn't need a separate room for. They're just kind of tucked away up in the ceiling. So it just really allows for a lot more options there. All right, and finally we're going to get our last case study today of this apartment we worked on. Last year's completed. It's still kind of finishing up some stuff, but it's a FIAS rated apartment building, super insulated, airtight, 5-story, 59 units, a mix of 1, 2, and 3 bedroom apartments. That was about 58,000 square feet. The system here was 12 outdoor commercial VRF units, individual ductwork system in each space or unit. Then it integrated a whole building ERV for fresh air. So here's the examples of what stuff looks like here. So this big one on the left is one of the outdoor units, providing, there's 12 of those, like I said, throughout on the rooftop of the building there. Here's one of the bigger duct systems providing to some of the common spaces on the first floor. Here's another kind of like laundry room or smaller cassette that's down in some other smaller spaces. And then this bottom right here is that ERV I talked about earlier. So this is a whole building ERV. These things work great. Again, just one central ERV to take care of all the fresh air needs of the whole entire building. And then here's just what it looks like in the apartment. So back to that, talking about space earlier. So this top left here is that's that air handler tucked up in there. It's got a little electric resistance booster in there for those coldest days where this heat pump can't take care of everything, but it's right above that's the entrance door there. You can't really see it. It's just really tucked up in the ceiling nicely there. Very small, tight package there. And then the ductwork just on this top right picture, you can see it just goes around the whole perimeter of that space for the supplies. And then there's just in the bottom right picture, you have the one central return with the filter right next to the unit there. And that's it. So a very simple, very minimal footprint, and provides very good heating and cooling, and can work in big and small operations. Just a very, very nice setup for that apartment building and what their goals were with that passive FIAS certification. And with that, that's our end of our presentation. And I'd like to thank you all for listening in today. And feel free to reach out to us at our contact info there. And I think we're going to open up for some follow-up questions as well.